So this is chapter 3, slide 60 that we're starting off today. And last time we had stopped on talking about nutrition because that's a major component of this course, health, nutrition, etc., right? Okay, so these are the different female and male categories right here for your age categories and how much on average you would burn. Is that going to be the exact same number for everybody? No. They're ballpark numbers, right? They're sort of median numbers, you can think of them, or averages, okay? People will be a bit different depending on a number of factors, right? However, this does give you a nice idea of where in the ballpark you should be. Anybody know why males burn more calories than females on average? Yeah. Basically, it's the resting muscle mass is actually the thing. And so you're just resting, even when I'm sitting here, having more muscle mass and more weight to move every time I breathe takes more energy. Yeah. So, yeah, that's that. These are the different energies that you would burn when you do different tasks on average. Again, people are more or less efficient. Funny enough, people being more efficient is in the United States of America is kind of a bad thing for you because we're just inundated by huge amounts of calories all the time, right? It's very easy to overeat calories in the U.S., right? Yeah. It's actually hard to get your nutrients and not overdo on calories. Yeah. We're crazy. Okay, so this is specific heat. You may have seen specific heat in various different places before. Your book uses SH for specific heat, literally the two first letters, right? That is not the only way to represent specific heat. You can also do CS, C sub S, okay? That actually is the correct specific heat right there. SH, I have never seen anywhere else before at all.
Which is going to be on our test.
I typically am not going to abbreviate it on the exam. It'll just be specific heat. Yeah. I don't know why it's like that in your book. But I could very well believe that there's 3 or 4 different specific heat designations. And I just haven't seen the other ones because I'm me. For whatever reason. So it's the different for different substances. It's different depending on the phase of your substance. Okay. So for example, solid water is going to have a different specific heat than liquid water. Okay. What specific heat is going to be is it's going to be how fast a substance will absorb energy and thus raise its temperature. Okay. So you can think of it a bit like the speed of heating. Right? Now, it's going to be, in terms of its units, the amount of heat, that is a joules number or a calories number, that's going to raise the temperature of that substance by exactly 1 degree Celsius for every 1 gram of the substance. Okay? So, for example, if I had 1 gram of water and I raised it 1 degree Celsius, then that would be, the amount of temperature would be the specific heat, wouldn't it? Okay. All right, typically it has these units. For the SI units, it's joules over grams degrees Celsius. Grams degrees Celsius are on the bottom. We can see that right here, actually. For the metric system, it's going to be calories. Notice it's 1.00 calories per gram over degrees Celsius. Hey, anybody notice that's 1? Guess what the definition of a calorie is? The amount of energy it takes to raise 1 gram of water, 1 degree Celsius, right? And so that was actually the definition of calorie. That is how calorie is set. That's the definition of calorie. It's also a specific heat of liquid water. Okay? That's what that always was. Notice that if you were to look at the conversion between joules and calories, that's actually that number right there. So whatever number of calories you have, it's times 4.184, and that gets you into joules, right? Because that's the only thing that changes between those two numbers, isn't it? Calories and joules. So that was just a conversion between calories and joules. That's all that was. If you look at specific heat again, here's the formula for that. You don't really need to memorize the formula, but you can if you like, or you could have it on your notes. It is, again, heat over the mass of the substance over the delta T meaning the difference in temperature, right? How much temperature you raised that, okay, or lowered it for that matter. So, note that the units actually tell you the exact same thing. Can everybody see that? This right here is energy, this is mass, this is the change in temperature, isn't it? Yeah. So I never bothered memorizing any of these formulas because the units actually tell you everything you need to know, right? Okay. So what is the specific heat of 24.8 grams of metal? It absorbs 275 joules of energy, and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius. Okay, so we're going to try to get specific heat, right? All right, so what is a specific heat?
It is specific heat is heat divided by mass.
It's heat, and so our heat is what? That right there, right? Okay. And so we're going to get that number, 275 joules, divide by. And then you said mass, and mass is what for units? It's in grams. So that's that number right there. Okay. And then we do change in temperature. You got it. And what is a change in? How do we do those? Yeah, and it's always final minus initial, right? Yeah. Where I end up minus where I started, right? Okay, and so I'm going to go 24.5 degrees Celsius. And then that's going to be minus the 20.2, and I ran out of space. Can everybody read that? Okay. Okay. And that entire thing is on the bottom, isn't it? Yeah. And so, notice that we're going to end up in joules over grams degrees Celsius, which is our units. Okay. So we go ahead and take that difference. That's 4.3, right? Okay, fantastic. Please note that you would not actually want to round anywhere but at the very end, right? Otherwise, it's going to cause you lots and lots of errors. Okay, so we go ahead and substitute these in just like we did before. That's right here. I've just simplified it with the 4.3 there now, right? Okay. And so I go ahead and do the math. I'm going to get 2.6 joules per gram degrees Celsius. It is 2 sig figs because of that minus right there. The change in temperature. Yeah, which is 2 sig figs. Yeah. That one was 2 sig figs, by the way, because when you subtract them off, the tens place disappears. Yeah. Yeah. This is a weird case where we actually lose a sig fig because we subtract off all our tens place, right?
Bless you.
Yeah. Bless you indeed. Okay, would anybody like an old-time treatment for sneezing, by the way? No? Okay. Should we hunt down the vampire? Go to the, so we would go to the cemetery. We would dig up corpses, torture them until one of them wakes up or twitches enough. And then we would drive a stake into the heart. This was cutting-edge science in the late 1800s.
I bet the twitching part got easier after we discovered electricity.
It would have definitely gotten easier. You are absolutely correct.
People panic at how many more vampires there were.
Yeah, there was over 300 patents, by the way, for vampire-revealing devices. If you look back in the records, it's pretty crazy.
God, it's such an easy time to scam people.
So it's joules
I mean,
per grams and degrees
Yeah, joules over grams degrees Celsius, exactly. And funny enough, like I like to laugh at old science, and we're like, haha, we're so much more intelligent. We're not at all, yeah. People were like putting on 4 face masks that face masks did not help at all for COVID. It was not like surgical face masks didn't help at all for COVID. And people were putting on like 4 of them, and it was getting into fights about it, and it was crazy stuff, right? Yeah. Like people lost their jobs and livelihoods over it. It was nuts. So, we are no better. Yeah. By the way, did you know that that's actually the source of vampire? Spelled with a Y. All the vampire movies and everything date back to that. There's actually newspaper articles about them. Yeah. Okay, so these are some different specific heats of different substances. Here we see things like aluminum, by the way. There's copper, gold. If we look into a like heat handling system that dissipates heat, what do you think that's typically made out of? So like over here, we see these numbers here. That's water, for example. And so water's not great at dissipating heat, but it's not terrible, right? Yeah. We start looking at things like copper, though, and that's a heck of a lot easier to move heat through, right? Yeah. Gold is even better, isn't it? But why don't they use gold usually?
Price.
Yeah, price. Yeah. And does anybody think they do use gold?
I bet they use it for specific things.
Oh yeah. Oh yeah. And very, very high-end computers they will. Yeah.
If the question starts with like Fahrenheit, do we have to convert that to Celsius?
You got it. Yep. Got to convert to Celsius. Perfect. Yeah, these will almost universally be in Celsius. You can get them in Fahrenheit. It's just very unusual. Okay. By the way, if you have a question that begins in Kelvin, on the other hand, you don't actually have to do anything special. Take the difference, whatever difference it is in Kelvin, it's the same difference in degrees Celsius. Okay? Because they have the same size of unit. Unfortunately, Fahrenheit does not. So, yeah, gotta convert that. All right, so because of the high specific heat of water, here we have water on a nice little coast there. If you have a large mass of water near a city or a location, you'll actually see that this large mass of water will absorb heat when it's very hot, and when it's cool, it'll start radiating that heat back out. Okay? And what that does is it severely limits the extremes of temperature that you're going to get. Anybody ever watch the Weather Channel at all? Or weather reports nationally? Yeah, seen those? Okay. Did you know it gets hotter in the Midwest during a number of days during the summer than it does in the Sahara Desert? It also gets colder in the Midwest of the United States than it does in Siberia. There's more extreme temperatures. The average is better, of course, but the extreme temperatures are actually worse. And the reason for that is there's not a lot of large water bodies in the area. And so the temperature does wild swings. Whereas like Siberia and the Sahara Desert actually have oceans fairly close. Not super close, but fairly close. And so kind of an interesting factoid, huh? That's why California has fairly moderate temperatures as well. A lot of coast. Yeah. That's that cool breeze coming off the ocean. So when the ocean water cools, the surrounding air is going to do what? Okay, when the ocean water cools, its temperature is going down, right? Yeah, somewhere else has to go up, doesn't it? And so the surroundings has to. Yeah, we got to warm that, don't we? Sand in the desert is hot in the day and cool at night. Sand must have a what? You got it. Very good. Very good. Yeah. Okay, so when we know the specific heat of a substance, we can actually rearrange that equation, and that will actually give us the heat equation. And that's why the heat energy is defined to that unit for heat energy, calorie. It's literally just a definition of specific heat, right? Okay, and so this is the heat equation in case you like equations and particularly love them so that you can memorize them or have them written down. And again, it's just heat equals the mass times the change in temperature times the specific heat. Notice that it's the exact same equation as before, just rearranged. So heat is by itself, and specific heat is now over on the right side. See that? That's all that's happened. Notice that the units actually just work out exactly like we had just talked. In this case, we're just going to cancel off everything but calories, aren't we? And so that's all you have to do if you ever want heat from a specific heat. You just cancel everything but the calories or joules, right? Which is the energy, the heat.
So for the calories, you put all those in.
So to get calories, you have to take the specific heat number, which has calories over grams degrees Celsius, and you have to cancel off grams, and then degrees Celsius. Okay. And all that's doing is this is just the unit workout for this. And they're all lined up together so you can see it easier. So if we plug in numbers with units here for each of these.
Could you actually work one of those out questions?
Yeah, we're gonna.
Okay, perfect.
Yeah, there's example problems.
Okay, so make sure.
You guys will catch on that that's what I do every time, right? I introduce something, so you have the underpinnings, then I work an example, and then ideally you guys will work examples and get immediate feedback because those are homework problems, right? Yeah. And that's kind of the best I can do in a lecture situation. That lab thing where you went through and the professor looked over your shoulder and went, this is what was wrong. That'd be a better method, but I can't do it for 44 people in the time we have in lecture, right? So use the heat equation to calculate the energy in kilojoules that's needed to heat 255 grams of copper from 24 degrees Celsius to 185 degrees Celsius. Mm-hmm.
Wait, heat equation, not specific heat equation.
Mm-hmm. It's the same equation, really. It's just rearranged.
But then in that case, would it be, 1 second.
Mm-hmm.
So 255 over,
So in this case, we're going to have to actually use the specific heat to figure out joules. Okay? And so what we have here is we have copper. We know what the metal is. We have a table up here that we can go to, right there, and get the specific heat. Okay? Okay, so let's go ahead and get the change in temperature first because it's just something easy to knock out. And we'll need that change in temperature no matter what, right? So we go ahead and take 185 minus 24. That gives us our change in temperature in degrees Celsius. 161 degrees Celsius. Okay, so now we can go ahead. This is the heat equation right here. Notice that's the same equation as the specific heat. We've just rearranged it so heat's on one side, right? Which makes it the heat equation. Because we can solve for heat. Heat's right here by itself. Okay, and so we look up the specific heat of copper. We have it right there. I've restated it from the table. I'm going to go ahead and plug it in right here. We got the delta T before. We just did that, didn't we? So we're going to go and plug that in. And then the final thing we need to do is we need to get that 255 grams of copper, and that needs to come down into the mass. Okay. So we've now plugged in everything but what we want to get. into that equation, haven't we? Okay. And so it's mass times the change in temperature times the specific heat. That would get us into joules. Is that actually what we want to get out at the end of this?
No, it's a kilojoule.
Yeah, we want kilojoules, don't we? So how do we go from joules to kilojoules again?
You gotta put joules on the bottom and kilojoules on the top so the joules cancel out.
You got it. And that's what I've done right there, haven't I? Okay. And so once we do that, we multiply across, then divide. We're going to get our answer. Notice that if you go through here, you can cancel all your units out and prove to yourself that you've done everything right. So we can go through, grams cancel the grams there, doesn't it? Degrees Celsius right there and there. So those cancel. Joules cancel. Yep. And it's going to be 3 sig figs because every single part of that is 3 sig figs, isn't it? Yeah. Mm-hmm.
And when it comes to the actual exam, will the specific heat be on it as part of the
Yes,
question?
most definitely. Now, it may not be in the question itself. I may give you a series of questions that all call onto one table, and then it's like in a table with other things.
So, but we will have like a reference. You won't have to like
Yeah.
memorize it.
No. The only one that you might ever be expected to have memorized would be the specific heat of liquid water.
Which is
1 calorie per gram degree Celsius.
well, that's easy to remember.
Yeah, because it's the definition, right? Yeah. And so you need that for the definition of a calorie. And so there may be an expectation of you like knowing what the definition of a calorie is, right? Yeah. So that's the only one that typically would have any chance of being needed to memorize. All the other ones will never be memorized. That's just a huge waste of time because there's a lot. All right. This right here, by the way, you really didn't need the formula, the equation. If you know how to work units, you have right here, the specific heat has to have been given to you because there's too many of them for you to memorize. There's literally millions of them. And that has units of joules over grams degrees Celsius. And so if you just want joules out of that, you can just cancel all the other units out, right? The only thing you have to remember in this case is that that right there is a change in temperature, isn't it? Which the problem itself has to give you. That's a range of temperatures, right? It's a change in temperature. Okay. So if you ever forget that formula, you didn't write it down, you whatever, you can just work units. Okay? All right. So let's talk about the changes of state. So when we're talking about matter, it undergoes a change of state, right? It can go from solid to liquid, right? And it could go back from liquid to solid. Everybody okay with that part? What's that process of going from a solid to a liquid? What do we call that? It's a change of state, but more specifically melting, right? Yeah, if that happened in front of you, an ice cube is doing what? It's melting. Okay, the other word for that is actually fusion. So if you have a bunch of ice cubes in a glass, what do? Fuse together into a liquid, don't they? Yeah. And so that's actually the other word for that. That would be fusion. Melting is the much more commonly used one, though. But you'll see fusion in just a bit. So freezing, that is going backwards, isn't it? Okay. If we then talk about going from a liquid to a gas, what does that do? Evaporation, or more specifically, vaporization. Okay. Evaporation being a form of vaporization. And that's why the words have the same root. Yeah. Yeah. Or vapor, right? Condensation, everybody's experienced this probably, especially in Tennessee, right? You have a cold drink out on your desk, what happens? Yeah, it sweats or condenses, right? Yeah. So condensation, that is vapor coming out or gas coming out as a liquid, right? That's that process. Okay, anybody ever seen dry ice?
Yes.
Okay, so when dry ice is sitting there, it goes directly from a solid to a gas. Does anybody want to argue that point with me?
Well, I've never once seen it actually have any liquid, so
Yeah. Every now and then I get people that argue because around here in Tennessee, if you just leave dry ice sitting there, it gathers water around it. And so you end up with liquid water on the bottom of it too.
Yeah, but the water didn't
Yeah.
come from the ice, it just got dragged in because the dry ice was actually sucking the moisture out of where it was.
You were exactly right, yeah. And it's just something that, yeah, when people don't realize that, they don't put it together. And so, cool. That process, by the way, is called sublimation. You go from a solid to a gas directly. You don't go through liquid. Okay? When you have the opposite, that's actually called deposition. Anybody ever heard that other than the legal term? Which is by far and away the more common one. Anybody ever heard that in a science context? Deposition? Okay. It's how computer chips are made. So if you look into it, like a computer chip for your computer or phone, actually is made through a laser deposition. Okay? Anyways, it's called lithography. It's pretty fascinating, actually. Check it out some. But anyways, that's the process right there. Okay?
A gas is always deposition.
Yep, directly to solid. Got it. Okay, and of course this right here is the 3 phases of water right there. And that's that process. So when we have a substance, it can melt while it changes from solid to liquid at its melting point. It will freeze when it changes from liquid to solid at its freezing point. That point where it freezes and melts, those are the exact same points. Okay? So 0 degrees Celsius is the freezing point of water. The melting point of water is 0 degrees Celsius. Okay? Think of it like this. If we had a room, solid in here, liquid outside, where would I exchange between those two places? The door. Is it a different place each time I go through one way versus the other? No, it's the same thing, right? And so when I'm talking about freezing points and melting points, if I started with a liquid, I freeze, right? And I call that freezing point. But if I go the opposite direction, and I could do that with the same sample, right? I could go from that solid back to my liquid, wouldn't I? And again, that would be the exact same temperature, same point. Okay? Okay. And so this is actually the process of melting and freezing. You're going from solid to liquid. Okay, that is melting. Notice that what's happening during that process is you're breaking about 20% of those interactions that hold the stuff together. So the solid is held together sort of maximally. That's why it's sort of frozen in place, right? And then you break some of those connections, and that gives you a liquid. See how they're broken, some of those connections? You can still see some of the same patterns, though, can't you? Yeah. Now we got liquid. Now, when we break those connections, that requires energy, right? Like you break stuff, it takes energy to do it. Okay? And so that's actually what this plus heat means, right? You have to add heat. That heat gets consumed breaking those connections. Okay? On the other hand, if you go from a liquid to a solid, you actually are going to lose heat out of that. It's going to heat everything around it. Okay? Anybody ever seen a condenser or a compressor? Yeah. Okay, anybody ever used like a tire compressor?
Yes.
Okay. You touch it after you used it, what does it feel like? Gets hot, right?
Yes.
Yeah. Okay, how about one of those cans with condensed air in them? Anybody ever used one of those?
Yeah. But it becomes cold, especially if you turn it upside down.
Yeah. If you spray out the condensed air in it, you're letting it expand back out, and so it's going to pull energy from around it. Okay? And that's actually the same thing you're seeing here on these. And that can help you out thinking about these things. So the heat of the fusion, that is going to be heat of fusion, is going to be that energy that must be added to convert exactly 1 gram of solid to liquid at its melting point. Okay? So when you're at a melting point, you can think of all the energy that comes in is going to be used to break those connections, separate out those solid molecules, and convert that to a liquid, okay? It's going to get all consumed by that, and your temperature isn't going to change when that happens. So for H2O, the heat of fusion is actually 80 calories, 334 joules. Okay. And again, that would be the energy that's required to melt 1 gram of ice, and this would be at its melting point, okay, which is where the ice would melt. So that right there would actually be what the equation looks like, or reaction looks like. So again, the heat of fusion, that is going from solid to liquid, right? And that is the energy it actually requires to break apart that solid into the liquid form for 1 gram. Now, this right here is actually the formula. So the heat equals the mass times the heat of fusion. Please note that the units here actually tell you everything you need to know about that.
It's just putting it in joules.
Yeah, you can do either joules or grams. You can do joules or calories, because either one is the heat. And you can convert back and forth, and that's that 4.184, right? Yeah. And so this is actually the conversion factors right here, if you ever need them, for all those. So those are the heats of fusions for water. And that right there is the workout of the units for that formula. Okay, and that's all that is. So how many kilojoules are needed to melt 32 grams of ice at 0 degrees Celsius? So again, I've done the same thing, haven't I? I gave you information that you're then going to immediately use, won't you? Okay? And so I need kilojoules, right? And so which heat of fusion did I want? Did I want the one in calories or joules? Joules. And do I want joules on top or bottom? I want to get into joules, so joules need to be on top, exactly. And so I want the joules on top number right there. Okay, so that's 334 joules for 1 gram. Of that water. Now, the next thing I need to do is I want to get into kilojoules. How do I get into a number that could go to kilojoules? Okay, fantastic. Yep, go to kilojoules, kJ, and joules on the bottom. And that's 1,000 joules for 1 kilojoule, right? Okay, and so joules are going to cancel. That's going to leave me in kilojoules per gram. Am I quite to my answer yet? No, I need to get rid of one more thing, don't I? Okay, what do I need to get rid of? Grams, right? And I have grams of ice right here, don't I? Yeah. So I just need to do 32.0 grams of ice on top. Those will cancel, and that'll leave me in kilojoules, won't it? Okay. Now please note that that was just working the units. I didn't bother with the formula, did I? I just went, I don't need a formula. The units will actually guide me in this. Now, if you want to use the formula, how you would use that is, again, you do what do I have, what do I need, how do I get there? Okay, I want kilojoules, I have grams. So if I go ahead and go, well, let's see here. I'm going to need a heat of fusion, aren't I? And so I would grab that heat of fusion. And again, these are the two conversion factor forms of that heat of fusion right there. Okay? Just joules is on top and one, joules is on bottom and the other. Okay, and that's right there is the kilojoules versus joules in case you forgot it. Okay, so the formula was again the heat right, equals mass times the heat of fusion. And so I just substitute those things in. And then, of course, I need to convert into kilojoules at the end. Okay. Notice you end up with the exact same thing. We just ended up in a slightly different order because we did the conversion first. So when sublimation occurs, we're going to skip that entire liquid step, right? We'll go directly into gas. So the particles on the surface of the solid are going to escape. They're going to use the energy that's put into them to escape that, kind of like a rocket blasting off Earth, right? And then they're going to start bouncing around, and that is a gas. Okay. Now, there's going to be, again, no change in temperature for this process. Now, keep in mind that that's talking about the substance itself, right? Whatever else we're talking about, it had to absorb heat from somewhere, didn't it? Okay? So, for example, if you took dry ice, the dry ice itself may not have a change in temperature happening, but you certainly are going to be losing temperature, aren't you? If you pick that up and touch it with your hands. So, in the reverse process, that's again going to be deposition, and that's where you'd actually have heat being given off in that process. And so, like, for example, those lithography systems for computer chips that use deposition, there's a huge problem with the heat. Okay? It gets very, very hot in there. It actually has flash heat. So, again, dry ice undergoes sublimation. Evaporation is going to happen when water molecules, in this case right here, gain sufficient energy to escape the solution. And those are what you're seeing escaping, for example, when you boil it. You're actually turning them into gas lower down, and then they are escaping out the top, aren't they? Okay. So this right here is the boiling point, and see it's 100 degrees Celsius. That's the boiling point. And so what's happening at the boiling point is all the energy is actually being used up to escape. If we were to boil a bath of water, what temperature does that stay at? 100 degrees Celsius. Does it matter that the burner's on it for 30, 40 minutes? No, it still stays at 100 degrees Celsius boiling water, right? What does happen, though, is the water level decreases, doesn't it? And that's because you're boiling the water off, aren't you? You're using all that energy up to launch those molecules up into the gas phase so they can bounce around and be in the gas phase, right? And thus you don't have any energy left over to cause the water to increase in temperature, do you? Yeah. And that's actually largely what water baths are used for. Like boiling water baths, doing things like boiling food in a baggie, right? Or you can take them and like heat up a pan above them, right? At 100 degrees Celsius so you don't burn chocolate. Okay? Cool. So in condensation, the water is going to, the vapor is going to go backwards, back into the liquid, and it's going to condense. You've seen this on condensation on your cold drinks, right? That's probably the biggest place you've seen it. Okay? And again, that's going to be the same temperature as boiling, but in that case, the heat's actually going to be removed from the water, and it's going to go off on the stuff around it. You've all experienced this. Has anybody had steam hit them? Yeah. And ouch, right? Got burned. That's because the heat escaped from the steam into you. Unfortunately. And when you looked at your wound afterwards, did anybody notice it was a little moist? Yeah, that's because the water actually deposited on you, and you had condensation on you, didn't you? Yeah. Oh my goodness. So the heat of vaporization, this is going to be the amount of heat that's used to absorb to change 1 gram of liquid to gas at boiling point. It's also what is released when 1 gram of gas changes to liquid at that boiling point. So when we talk about one of these processes, think of it as going up and down stairs, right? So when we're launching these molecules from the liquid phase up into the gas, it's like going up the staircase, isn't it? We have to use energy to do it. Okay? Putting that at a high energy state. Okay. So when you go down the staircase, did the number of stairs change? Sometimes it may feel like it. But the number of stairs is the same either way, isn't it? And so the energy of these two processes, when you're going from the liquid to the gas, you're going from the gas to the liquid, that amount of energy is the same. The only difference is the direction of it. Okay? When you're boiling something, you're using that energy up to go into the gas. When you're going the reverse direction, it's getting released. Okay? Same thing for freezing versus melting. The amount of energy, the exact same. It's just the direction of energy that changes. Okay? Is that making sense so far? Fantastic. This is true everywhere all the time, by the way. I won't go into it in great detail because we don't have time to go into it in a huge amount of detail. But energy is neither created nor destroyed. You may have heard of that before. Yeah, same thing, right? If you have a similar process, it typically takes the same amount of energy to go one direction as the other. And these would be called state functions, actually, because all that matters is the end state. Okay, so this is the amount of energy for water going from a liquid to a gas or a gas to a liquid. All that would be different is the direction the energy goes. Okay, and notice that number is quite a bit larger than the previous heat of fusion, isn't it? Okay. All right. So this same amount of heat is going to be released when we have 1 gram of water vapor that changes to liquid at 100 degrees Celsius again. So again, this would be the heat of condensation as well. They're the exact same numbers. So heat of condensation is going from the vapor to the liquid. Heat of vaporization is going from the liquid to the vapor, right? They're not separate things, same amount of energy, just different direction. Okay. So, again, this is the heat of vaporization. Now we're just showing it in the different units, and we're flipping them both ways, just in case you forgot you could do that, and etc. Okay. I know. This is that same formula, by the way, because it's the exact same units, same formula, same sort of process. It's just a larger number in this case because we're going from liquid to gas or gas to liquid. Okay? No real differences. So how many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? Okay, so what do I have? What do I need? How do I get there? I have that mass of steam, right? Okay, and I know that steam is going and it's condensing, isn't it? So that tells me I need the heat of condensation, don't I? Okay, which is the same number as the heat of vaporization, so either way. Does the 100 particularly matter here?
Not really.
So the 100 is only used for context. It tells me that we're at the boiling point, right? And so that heat of condensation, I can use that without worrying about anything. It's that number. Okay? It's not actually going to be used in my calculations, though, right? Don't need to worry about that. Okay, and so what I'm going to do is I'm going to get that heat of condensation. I want the unit in kilojoules, and so that means the one that's in joules, that's the one I want, isn't it? That joule number, should it be on top or bottom? Top, you got it. Okay. And so I'm going to get that number. It's right here. And the one we want specifically is that one, isn't it? Okay. And then we need to get this in kilojoules, don't we? So we want the kilojoules on top, joules on bottom number. We're going to multiply those two numbers. So right there, being the heat of vaporization or heat of condensation. Right here being my prefix conversion, going from joules to kilojoules. And finally, we need to get rid of grams of water here. And so we take the 50 grams of water and we use that. Okay. Did I lose anybody? Okay. So the 50 grams of steam, we go ahead and put that down, right? 50.0 grams of water in the gaseous form. Okay. And so we're going to go ahead and use the heat of condensation, 2,260, and that's joules, over 1 gram of water. Okay, note that that will cause grams to cancel, leaving me in joules, right? And then finally, I just need to get that in kilojoules, which is what my final answer wants. And so, 1 kilojoule. Whoa. I need to restart my computer. 1,000 joules. There we go. Okay. I just reworked that. Okay, and then we get the final answer, 113 kilojoules. Notice that everything else is exact numbers in here, except for these two, which are both 3 sig figs in this case. So. All right, so let's talk about heating curves. Some of these processes are going to be more complex than just one conversion, right? For example, if I heat up a pot of water and then I boil it and then that water goes off and condenses somewhere else, that's a more complex process than just one step for the calculation, isn't it? Okay? And what you need to realize and understand is these heating curves are the probably best way to understand that process. Okay? It greatly helps you demonstrate it. And so the heating curve here, we have these right here, which are the diagonal lines. See that right there? Where the solid. What we're doing here is we're actually heating the solid from negative 40 degrees Celsius up to 0 degrees Celsius. Everybody see that? And when we do that, we're not going to have any real phase change happen. Okay? We're just going to heat the solid up. All the energy we put in heats it up and causes the temperature to go up. Now, what would I use in the case of where I'm heating things up and how fast they heat up? Remember this specific heat? Yeah, that region would be specific heat dependent. Okay? That slope here, that's the specific heat. Okay? Okay, now when we get to this plateau, everybody see the plateau right there? Okay, that temperature is 0 degrees Celsius, isn't it? What's happening at that plateau? So we had ice, 0 degrees Celsius, we're adding heat to it. That's the melting point, right? We're melting it. And so this process, the reason it plateaus right there, is that is the process of melting that block of ice. Okay? And all the energy that's being put in from our Bunsen burner under it, that is actually just breaking apart those connections and making it into liquid water. Okay? Okay. Can everybody see it okay? Fantastic. And this is why, for example, you can make an ice bath and it will hold that temperature for a bit, won't it? Yeah, it'll actually stay at around 0 degrees Celsius. Okay? Because you're actually on this plateau and it's slowly melting, right? All the heat is getting used up and melting. Okay. So the next part we're going to do is we'll have liquid water. It's at 0 degrees Celsius, and we're going to put heat onto it. And what's going to happen is it's going to warm, isn't it? Yeah. And so we see our temperature go up. And again, this is just that warming. The heat we're putting in is going to raise the temperature. We'll have no real phase changes happening. Okay? And so next would be this plateau. And this plateau is what?
That's the boiling point.
It's the boiling point, 100 degrees Celsius. So again, we hit the boiling point. We're going to go from the liquid to the gas. All the energy we're putting in is doing what?
It's heating up.
Yeah, we're breaking apart and causing that liquid to go into the gas, right? That's where all our temperature is getting consumed. And so it plateaus. It doesn't really go up in temperature Okay. Now, please note the next step right here. This is going to be heating the gas, right? And so this would be how you get water up into the 400 degrees. Is you'd have gas, the vapor, and you'd heat the vapor, and it would end up in 400 degrees, right? Okay. Now, please note that there is a minimum here. Does anybody know what that minimum over here is? The coldest you can cool that ice.
-40.
0 Kelvin. We basically never bother going below what we absolutely need to here, because it just goes down to 0 Kelvin eventually, and then that's the lowest you can go. Okay, because that's absolute zero, right? Which is negative 273 degrees Celsius, right? Okay, how about this temperature up here? Is there any maximum that you can take that steam to? So in our current chemistry, we know here in this class, there would not be, right? You could basically keep going forever. There actually is a maximum where you'll start turning it into things like plasma, and you'll start ejecting all the electrons from it and fusing together the nuclei. That's how like reactors work, nuclear reactors. Like the sun works. So, but that's way up here, and we'll never even think about going yet there, okay? We will talk a bit about nuclear, though. Now, does anybody have any questions about these at all? Would a real-world heating curve look exactly like this? No, the real world has imperfections, right? And so the real world, this plateau would look something like that. A very mild upward direction. Almost not there, but yeah. Because it's not going to be quite perfect, okay? Okay, this is a cooling curve. Honestly, that's the last time you'll probably ever hear me say cooling curve, because it's just a heating curve that's been flipped, isn't it? Yeah, it's the exact same thing. We're just going from high temperature to low temperature, right? And so I will refer to these as heating curves all the time. Yes, that is somewhat bad English, but it's the same thing, right? Okay. Now, a plateau horizontal line on a heating curve represents what? Temperature change? Constant temperature, that's exactly right. And what else?
Change of state.
Yep, change of state or boiling or melting. Yep, that was exactly right. And so, yeah, that's exactly perfect. A sloped line on a heating curve represents what? A temperature change. These other ones? Nah, those are wrong. Okay, fantastic. How's my time looking, by the way?
You got about 17 minutes.
Okay, okay. Using the cooling curve for water to answer each of the following, water condenses at a temperature of what? Okay, so what's the opposite of condensation? Boiling, right? Yeah. And so what's the boiling point of water?
0.
Not 0, but
Or that's the freezing.
yeah.
Boiling's 100.
100 degrees Celsius, right? Yeah. And so if you ever get a place here where you're like, condenses, I don't remember that one, just flip it. Because it has to be the same point exchanging between the two, right? If you're going between two places, it's always the same point in between, right? So, yeah. At the temperature of 0 degrees Celsius, liquid water does what? Freezes. Does it do anything else? What if you start with an ice cube? Can it freeze more?
No, but going the opposite, it could melt.
Yeah, it could melt. And so remember that these, the temperature 0 degrees Celsius, the temperature 100 degrees Celsius, those are the points at which you go back and forth. Okay? Mm-hmm.
I kind of argue that just being frozen into ice isn't quite as frozen as ice can get. I mean, like, think about the difference between, like, say, an ice cube from the freezer and a similar sized chunk of ice that you take off a glacier or something. You really think there wouldn't be a difference there?
Oh, no, there isn't. There actually isn't. It depends on the purity, of course. and it depends on how you froze them, what it looks like, but there wouldn't actually be a difference between them. It does. And one is not more ice than the other. What you're kind of thinking of is that the process of freezing is not completed at one step, but you're actually thinking about what I just said, which is that when you're at freezing points, that's actually the changeover point. Okay? Yeah. You okay? Okay. And so just remember that the freezing point, that's the changeover point, right? The boiling point, that's the changeover point. It's the point at which you'd be at an equilibrium, balancing between the two. Okay? You can push it more one direction or the other by going a lower temperature, and so you do. Like your freezer is not 0 degrees Celsius, right? Your freezer is actually lower than that. Okay? Your fridge is actually almost 0 degrees Celsius. Yeah.
So wouldn't this just be freezes because it's specifying that it's liquid water and it can't melt? It would have to be ice for it to melt?
Yeah. Technically, it would be freezing at first, but because we're at 0, we will exchange back and forth.
So this answer would be both A and B.
Yeah, we'll have both processes existing. Though, yes, you are correct. The first thing it does is freeze, and then we'll get an exchange back and forth. Okay? So at 40 degrees Celsius, the water is what? Yeah, liquid. When water freezes, heat is what? Removed. Yeah, we're taking heat away, aren't we? Okay. Anybody ever felt the back of a fridge?
Yes.
Yeah.
I can't remember.
Or the back of an air conditioner? The other side of the air conditioner? No?
It's warm, right?
Yeah, it's warm.
Okay.
Yeah, exactly. You got it. So they're both warm, right? And that's because what's happening is you're pulling the heat away from what you're refrigerating or you're cooling, right? Okay. Okay, so a 175 gram sample of steam at 100 degrees Celsius is emitted from a volcano. It condenses, cools, and falls as snow at 0 degrees Celsius. How many kilojoules were released? Ooh, this is a bit more complex of a problem, isn't it? Yeah, this isn't going to just be one of those calculations. This is going to have to be actually a series of those. First thing you should do is you should go ahead and set up a heating curve to help you think through the process. Because we always need to document, what do I have, what do I need, how do I get there, right? Formal problem solving. And so we have steam. It's at 100 degrees Celsius starting off, right? Okay. So the first thing we have is 100 degrees Celsius. And that's steam, and the first thing that's going to happen is condenses. See that? And we'll have a plateau here, won't we? Okay. By the way, did anybody notice the plateaus, the difference in their sizes?
Yes.
The condensation / boiling was a lot longer, wasn't it? Yeah. That's because of those heat diffusion versus heat evaporation. Yeah. That if you measured those out and compared them, that's what that would be. Okay. Okay, so we have this first region right here. That's condensation, isn't it? Okay. And that's going to be a phase change. And so that's a phase change problem, right? Okay, phase change problem. The next thing that's going to happen is it's going to cool, isn't it? And cooling is going to be a diagonal line. And that's going to drop you down to 0.0 degrees Celsius, isn't it? And so this is the second part of this, and that's a specific heat problem. That's liquid water. Are you guys comfortable with SH or CS for specific heat?
SH.
SH? Sure. That's fair. That was a very strong opinion, which is fair. Yeah, that's one of the reasons why I use, even though they're incorrect symbols, from your book, I still put them in. Because, yeah, this is like your first exploration of the matter. So we go ahead and get to the next part. So it falls as snow. What is snow?
Ice.
It's ice, right? Yeah. And so we have another phase change, don't we? Yeah, and that's that third region. And we are ice, ice baby. Sorry. Yep. Yeah. Okay. Now, so we're trying to now figure out the kilojoules that's going to be released, aren't we? Okay. Now, let me point out this graph here, that's temperature over here, and over here, that would be the heat, or otherwise known as kilojoules, right? Energy. Okay? So if we look at this graph, where is the majority of our energy going to come from? Yeah, one, the phase change there, right? Okay. If you're on a test and you're like running, you have like a minute or something, do the phase change for going to gas or coming from gas. It's always going to be the largest section of this. It's always going to be like half your energy or more. Okay? Because it just takes by far and away the most energy to go to gas, and by far and away that releases the most energy. That's why when you get hit by steam, it hurts a hell of a lot more than just getting hit by 100-degree water. Okay? It's because there's just a lot of energy in it if you're getting hit by 100-degree steam. Okay. Now, we're going to go ahead and do this process. So this first phase right here, where we're doing this phase change, that's going to be a heat of condensation, isn't it? So we'll need the heat of condensation, and we'll do a heat of condensation problem. This second part, we'll need the specific heat. For what, though? Is it liquid water, solid, gas? It's liquid. You got it. And so we'll need the liquid specific heat, right, for water. And then finally, the third part, we're going to need that phase change for ice, or another way of saying that would be the heat of freezing or heat of fusion, right, which are the same numbers. Okay, so this right here is just the same thing I did. I just drew it out. Here's our units right here. So right here we have that heat of fusion, right? Are we going to want the one with joules on top or joules on bottom? Joules on top, right? Because we want to go into joules. So we're going to need this one. How about specific heat? What are we trying to get out at the end of this? Yeah, we're trying to get energy, right? So we want the specific heat that is in joules on top. Okay. And then finally, we have the heat going from the liquid to the solid, or freezing. And we want what? Joules on top again, right? Okay. So those are going to be the ones we need to look up and get. Okay. And then this is just converting from joules to kilojoules each time, which is this right here. Do I actually have to do that each time? No, I could do that at the very end. Okay. Yep. I could do my unit conversions at the very end. So let's actually go through and do these processes. So right here, this is that first step that we talked about. And we're going to go ahead and take our mass of our water, 175 grams. We're going to multiply that by, again, our heat of vaporization right there. And then in this case, we're just going to go ahead and convert it into kilojoules because it's usually easier for people to follow if I do that. Okay.
Where did you get 175 grams from?
The very beginning of the problem.
The vapor that he gave us.
Oh, okay, I'll see it now.
And we had to go and get the other one.
Okay. All right, fantastic. Now, that gives me 396 kilojoules if I round it to the correct number of sig figs. Should I actually have rounded it to the number of sig figs at this point? No. Yeah, that was a bad idea, right? Okay. Naughty. Bad, Dr. Clausen. Okay. Now, the next thing I'm going to do here is I'm going to go ahead and take that change in temperature, right? I'm going from 100 degrees Celsius to 0 degrees Celsius, aren't I? Okay? That is a 100 degrees difference. So 100 degrees Celsius is our change in temperature. This is going to be useful for that second region, right? Where we have the change in temperature. So I'm going to take, again, that mass of water, 175 grams. I'm going to multiply it by the specific heat, 4.184 joules over gram degrees Celsius. And I'm going to multiply that by degrees Celsius, 100 degrees Celsius change. Okay, that'll get me into joules. I then take that number and I convert it into kilojoules. Okay, did I lose anybody in that? Okay, and notice that's exactly like the specific heat problems I did before. It's just I'm combining all those problems together, aren't I? Yeah. Okay, so the last region is this one right here, and that was my region 3, the fourth step of the problem. And so I'm going to take 175 grams. I'm going to multiply that by the heat of fusion right there, which is the 334. And then I'm going to divide it by 1,000 so I can get into kilojoules. Now the thing I want to go ahead and show you here, this is 58.5, this is 73.2. That one right there is 396, isn't it?
Because that's the most heat.
Yeah, that's the most heat you're going to get. So really, if you just do whatever has the gas phase in it, phase change, that's going to be your biggest source of heat. Okay? Okay. So that is very close to the answer. All I need to do to get the proper answer is to add those together. And I get 528 kilojoules. I go back to my ABC there. And it is this one right here. Now let me ask you a question. I have 1 minute to do. Is there any way I could have gotten this done in 1 minute?
Yeah, because it's multiple choice. If you find out the first one,
You got it.
change.
Yeah. If I figured out the gas right here, I know it needs to be larger than that, don't I?
So the other two choices were less than 396. Or so close that.
Okay, folks, we're going to do an exit pass. So please take out your clicker, and you're going to answer A. And you can actually do it while you're sort of walking by if you want. Just need to double check it got done. Thank you. Hand, please. Thank you. Go. I think I got everybody right. Fantastic.
There's a way I can go on those directions online to download the book and everything.
Yeah, though if you want to do it real quick, it's pretty fast.
Okay, I have to run catch Dr. Macy.
Oh, okay.
But I'll just shoot you an email if I'm struggling with it.
Sounds good. Yeah, okay. Oh my goodness. Send me an email that Dr. Lawson, hey, I was there.
Okay.
Remember me. Okay.
Facebook, it might be easier texting you on Facebook or something. I didn't see my name.
Oh, send me an email going, hey, I was here, remember me.
Yeah, I didn't get to mine either.
You too.
Okay.
Yeah, email, hey, I was here.
So the test is over chapters 1 through 4.
You got it.
Perfect. Thank
Perfect.
you.
Oh yeah. Okay, perfect. Okay, I'll just message you on there. We can do like a chat on there.
Oh, did you not get scanned before?
No, it didn't.
Okay. Send me an email going, hey, Dr. Clausen, remember I was there.
Okay.
Okay?
Perfect. Thank you.